We are live. Welcome back, everyone. Today we have a very exciting lecture. This is the Orgo Rapid Review. Hopefully, we get to put Orgo in the dust with this one, but that means that we are in for a very long lecture. Okay, so I realize that I didn't really make a disclaimer for all the people watching back home. The Rapid Review series is going to be its own playlist because the Rapid Review is specifically meant for students who are close to the end of their content review, near or at the end of their content review, and also for students who are going to take their exam very soon and just want to brush up on high-yield topics to see whether or not they have things that they are, that they have content gaps in. So this series, this Rapid Review series for all of the different sciences that I've taught before, is supposed to be after your holistic content review, which is something we've done in the lecture. If you've been in the lecture the whole time, like David over here, you've seen me teach pretty much the entire science curriculum on the MCAT, so except for physics. So the Rapid Review section is specifically for students who are nearing the end or at the end of their prep. Please, that's a huge disclaimer because I do not want to confuse you if you guys come and see the Rapid Review video as the most recently uploaded video and start watching it and get overwhelmed and then start crying because you don't know what I'm talking about. So for the Orgo Rapid Review, you must have watched the entire MCAT organic chemistry playlist and or have a great familiarity with the concepts therein. So that as a disclaimer, thank you so much for watching. So let's get started. Of course, we need a title, and this is the Organic Chemistry Rapid Review. All right. So where to start? Actually, I don't know. Let me pop open my notes. But I assume we're going to start with some naming, because that's where everything starts. Learning the alphabet, right? All right. So nomenclature. Nomenclature, I really don't feel like we have to spend a crap ton of time on, but there are certain specific things about nomenclature that I want to go over, right? So different functional groups, right? So this functional group versus this functional group versus this functional group versus this functional group versus this functional group. All right, and then this one, and this one, and this one, and that one, and you get the point. So you should be able to tell me what all of these are called. What's this one called? A carboxylic acid. And that's a COOH, right? That's the way you sort of denote that, right? COOH. What about that guy? Well, carbonyl, but specifically a ketone. When a ketone is not top priority, what prefix do you give it? You give it the prefix oxo. Right, and I realize I probably shouldn't write this because we're just going to put the prefixes right here. Right? Oh, this is the same as the other one. Oops. There you go. What's that? It's an ester. Right? This is an alcohol. Suffix ol, all. What's this? Phenyl. A phenyl group. What's this? Anhydride. What's this? If that's an ester, this is a thioester. Also, talking about thio, if that's a thioester and that's an ester, this is an alcohol. Does anyone know what this is called? A thiol. And sometimes the MCAT in a passage, they'll say thiol, and you'll have to kind of recognize that that's what they're talking about. But another thing they'll say is the phrase mercapto. Mercapto means sulfur. Whenever you see mercapto, it means sulfur. What's this? Acid, specifically chloride, but yes, if it were any of the halogens, it would be an acid halide. So this is an acid chloride. That? Amide. And this? An amine. What about this? Enamine. Enamine. Or sorry. Enamine. And this? Imine. Imine, enamine, amine, amide. What's special about this? What's the hybridization of that nitrogen? sp2. Why? Because it looks like it's sp3. 1, 2, 3, 4. Why isn't it sp3? The lone pair of electrons actually resonates like this. Could you imagine not having studied organic chemistry and then I start like this? This is why you need to go watch the Orgo videos before you do the rapid review. Sparkling water is so good. All right. Yep.
In that form it's sp2, but in the resonance form, is it both sp2?
So that's an important question. That's a really important question, actually. So let's zoom in on that. So the question is the nitrogen, if I'm understanding your question properly, Joseph, is the nitrogen sp3 or sp2 or both? Yeah. Right? Let's take a look. I'm going to take my ring off because it's scraping the board. Sorry to my imaginary wife. So the question is, when we do resonance like this, is the nitrogen sp2 like it looks over here, or is it sp3 like it looks over here? And a better way to visualize that is to actually draw out those hydrogens, because it's easier to see how they're sp2 or sp3, right? So here the nitrogen is sp2, and here the nitrogen is sp3, because that last domain is the electrons over there. Well, the same thing can be said about the oxygen. Right? So for both of them, are they both sp2 and sp3? Are they both sp2? Are they both sp3? What is it? Right? Do we just look at the neutral and base off of that? Do we look at the resonance contributor based off of that? Here's a question. I want to make soup. I want to make soup, right? And I have the chicken bones and the vegetables, and I have the spices and everything. I have no water. Can I make soup? No, I can't make soup without water. You need water to make soup, right? What do you need in order for resonance to happen? What do you need? What does resonance require? P orbitals. It requires p orbitals to move through. Do sp3 atoms have free p orbitals? No. So if this nitrogen were sp3, it would not be able to resonate. So it can't be sp3 because we know it resonates. It's not that we know it's sp3 and it somehow resonates. It's that it resonates and we know that, so it has to be sp2. Can't make soup without water. You can't do resonance without a free p orbital.
Just remind us, we have to go over the pKa tables and stuff.
Yes, we do. pKa table. Correct. Thank you. That was from last time, correct? Let's go over some more strange and unseen functional groups. It's a hydrate. But yes, it's also known as a geminal diol. It's a hydrate, right? This is an aldehyde hydrate, and this is a ketone hydrate. Hemiacetal. Right? Hemiacetal. And acetal. If that's a geminal diol, that is a vicinal diol. Very good. Okay. Now, when we talk about hemiacetals, sometimes it's hard to see exactly where this happens until someone takes it and rewrites it a different way. This R can be anything, right? He said the R could be anything. Glucose in a ring form is a hemiacetal. OH, OR, H. Hemiacetal. All because we took this and turned this whole thing. It's just that those two R's are connected. Okay. That's functional groups, right? Next, big thing here. R or S. R. 1, 2, 3, R. R or S. This is a hard one.
R.
Why? All right, so BR is going to be number 1, right? And then
SH is going to
2,
be 2, the ring's going to be
3.
3, and that one's going to be 4. But
This goes S.
yeah, but the first priority group is in the back, so gotta flip it, it's going to be off.
So I take your word for that. But to be safe, I always rotated the molecule so that the 4th group is in the back. What's the 4th group? It's this guy, right? I'm going to send this guy to the back. So by sending that guy to the back, what's going to happen is I'm going to get BR in the front, this guy in the back, right? And then I'm going to have, on the line, I'm going to have SH. So now I can go 1, 2, 3, and comfortably say R. I can comfortably say that that is an R compound.
Can you explain why SR is different than a conformational isomer?
Because a conformational isomer are molecules, I have it right here, that can twist and turn into one another. So what's the best example of an R and S enantiomer in real life? You're writing your left hand. You're writing your left hand, right? And mirror images. Put up your right hand in front of you. And now put up your left hand in front of you the same way. Twist your left hand to match your right. You can't. It's not possible. I would have to chop off your left hand, invert it, mirror it on its axis, and then it would match your right hand, right? So there's no way, in the way that it's attached right now, to twist it to make it look like your right hand, right? And since that's true, they are R and S of one another, right? So let's look at an example. R2-butanol. What's that? If that's R2-butanol, what's that? S2-butanol. You're like, Yusuf, you drew the same thing twice. Did I? No, I didn't. Because if you take this and you make it look like that, so if I take my right hand, I take my right hand and I take my left hand, if I try to make my right hand look like my left, watch what happens. I have to twist this along that axis, along this axis, 180 degrees, right? Let's do that. That's going to go to the back. These might match up. The OH doesn't. And neither does the H that no one ever draws in. Just doesn't match. Oops. Yeah. R and S2-butanol. You cannot twist them to make them look like one another. What is an example of a conformational isomer? Well, a boat and a chair. The boat can flip its leg down and become the chair. Another one. That and all you gotta do is take the front plate and twist it 120 degrees. That's it. Newman projections, great examples of conformational isomers. Change conformation and they become the same. Good? Cool. Now here's an interesting question. oftentimes on the MCAT, they'll give you these little compounds, right? Let's stick with R2-butanol. And they'll say, you took this guy and you added tosyl chloride. And then after adding tosyl chloride, you added, I don't know, what do we want to add? Cyanide. KCN. You added tosyl chloride and KCN. And they ask, what is the name of the product? And answer choice A and B and C and D look like R, S, R, S. What are you picking? Why?
Because the tosyl chloride is a backside attack, no? So it changes the, forgot the word.
Not the tosyl chloride. So the tosyl chloride actually makes a leaving group out of the alcohol, right? Tosyl chloride makes a leaving group out of the alcohol. How? Well, here's tosyl chloride. That's tosyl chloride. And when it reacts, the intermediate's going to look like and now you see how that's a good leaving group? So when the cyanide comes, and backside attacks that, the cyanide's going to end up where? In the back. So the inversion of stereochem happens at the second step. But you are absolutely correct that you're going to pick S. So immediately, you can get rid of 2 of the answer choices. And now you have a 50% chance of getting it right, even if you don't know what happens. This is a test of strategy. Be smart. And since you put a cyanide on it, what has to be in the answer? Cyano. Someone name that compound. We just said S. That's 2. Cyano. Butane. S2 cyanobutane. Very good. What is a meso compound? Isn't that the $1 million question?
Compound like symmetry. If you rotate it, flip it 180 degrees.
It has chiral center.
It's a compound with chiral centers that is achiral. It is a compound that has chiral centers, but is in and of itself achiral.
It's achiral because it has symmetry.
It does. A very good example is this. That's a chiral center, and that's a chiral center. There's a center of symmetry right here. Because if you go to the left and out, and if you go to the right and in, you get the same thing. Or you could rotate this. So you could take this compound and say, I know there's free rotation about that bond. And you can make it look like this. Mirror plane. And since it's the same on either side of the mirror, the rotation that is given by the chiral center is canceled out by the other chiral center. The rotation of what? Plane polarized light. That is the definition of chirality. Something that rotates plane polarized light. Right? Okay. Let's get into the nitty-gritty of today's lecture. Let's do some mechanisms. If you guys would like to grab some treats, please feel free. At any point during the lecture, because I'm just going to keep yapping for like 2.5 hours, so. Because I don't need breaks. Yes, I do. That's a lie. First reaction we're going to look at. The SN1 reaction. The most, not the most classic, but one of the most classic reactions in all of organic chemistry. I would vouch to say that the SN2 reaction is more classic than the SN1 reaction. This is unimolecular, nucleophilic substitution. What do we mean by unimolecular?
The rate depends on one.
Yeah, that's a slow step. All right, so what do we need for SN1 to happen? We need a good leaving group that is either secondary, tertiary, or allylic. And we need a polar protic solvent. What are polar protic solvents? Water, ethanol, other alcohols, etc.
Polar protic solvents are the ones that are capable of hydrogen bonding? Is that, am I remembering that correctly?
Yes. Because they're protic, correct? So let's take a good leaving group, a tertiary good leaving group, right? And the first step of any SN1 reaction is the leaving group leaves. Leaving group packs its bag, fucks off. Reversible reaction. And the formation of the carbocation is the rate determining step. So if you were to write a K expression for this, there you go. Next, your polar protic solvent will attach next. You will get deprotonation of the adduct by what? Another solvent molecule. Why not the Br? Because the solvent is in excess. It is in excess. Classic SN1 reaction. What's one way I could increase the rate of this reaction? What is one way I could increase the rate of this reaction? Well, I could increase the stability of the beginning species by doing that. Right? Because now that carbocation can resonate.
And that's a secondary allylic.
It's tertiary allylic.
What's other?
Adjacent to a double bond. Adjacent to an sp2 carbon. Now, between the two of those, which one's going to be the major product? The major product is still going to be this guy, because the tertiary carbocation is more stable than the primary. And remember, primary carbocations don't exist unless they are allylic. You know what really doesn't exist? A vinyl carbocation. What is that? That doesn't exist. Why not? Someone explain to me the chemistry behind why that doesn't exist. Well, first of all, it's not resonance stabilized because it's not in a conjugated system, right?
There's no free p orbitals.
There is a free p orbital. Every carbocation has a free p orbital, right? But why can't that exist? Well, if you look at the double bond right here, the double bond already has a p orbital. And p orbitals are what? Finish the sentence. P orbitals are, I've said it a couple times in lecture, p orbitals are electronegative. P orbitals are electronegative. They want electrons. So if you plop something on top of here that's going to start stealing electrons away from the p orbital, it won't be too happy. It's a very, very unstable species. You don't want that to happen. Let's go through another consideration. And you guys are going to do the reaction by yourselves and tell me what you get. That means slightly acidified, right? (37°). Do the reaction. Let me know what you get. Who wants to get us started? Anyone feel confident enough in their abilities with organic chemistry to teach the class? All right, so what do we do first? What's the first step of every reaction? Leaving group leaves, right? What about now? Yeah. So every time you form a carbocation, you have to look around it and see, is there a better position next to it where it could be living? So this position is worse than secondary, but that position is better. So what's going to happen is that there's a hydrogen here that's going to hop one position, and that's called a hydride shift. And I have absolutely no idea how this actually happens, but that's what happens. And now that the carbocation is in a new position, you have to ask yourself the question again. Could it be in a better position? No, it can't. There's no better position on the molecule that it could be. So now all of those steps are going to happen, and your final product is actually going to be this. Hello, everyone. What's going on? Don't worry, we didn't get to the exciting stuff yet.
It's O right?
Sorry?
Not OH.
OH, yeah. No, OH. Oh, sorry, yeah. OET. There you go, my bad. Do you guys want to come down? We're going to do a lot of drawing this lesson. So just come down one flight, and you might be able to see a little bit better.
Can you go over later? That was some reaction of base catalyzed.
Yeah. We'll go over that later. So like the aldol condensation is a big base catalyzed reaction, and then alcohol dehydrations are acid catalyzed reactions. We'll talk about what we mean by catalyzed reactions. Right. This you don't necessarily need to worry about. But why do we put slightly acidic conditions here? Fun fact. Carbocations are acidic. Someone validate that statement for me. Prove that statement to me. carbocations are acidic? Because I could just say, I could be lying. I could be completely manipulating all of you and saying that carbocations are acidic. Someone prove that statement. Well, in order to prove this statement, you need to know about the laws of chemistry, correct? And the theories of chemistry. And for acid-base theories, there are two different theories. Number one is a Bronsted-Lowry theory, and number two is a Lewis theory. The Bronsted-Lowry theory states that anything that can donate protons in solution is acidic. The Lewis theory states that anything that is electron deficient and accepts electron pairs is acidic. Anything that is electron deficient and accepts electron pairs is acidic. So acidic conditions are favorable for carbocation reactions, which makes perfect sense. You didn't miss much.
My first you find her here.
Good. I remember her from last semester.
Yeah, she's the one that got me here. Now I've been here with after.
This is pretty much, we did this and then nomenclature. So carbocations are acidic because of the Lewis acid-base theory, the Lewis theory of acids and bases. David was here earlier. Other David, not this David, but David was here earlier, and he didn't even recognize me because... All right. So naturally, after SN1, what comes next? No. E1. Let's do E1. E1, unimolecular elimination. Same rules as SN1. One more thing. A little bit more heat. Spice things up a little bit. So an E1 reaction will look like a triangle underneath. Put that thing over a flame. First step. Mm-hmm. Then?
The beta hydrogens,
Good.
right? One of them gets blocked off.
Which one?
Whichever one's going to make it more substituted. So the one on the right.
Yeah. So we have HA and we have HB, right? Let's actually do both. Let's try both. Right? And then also something's missing. Something's missing.
Rearrangement.
No. Something's missing. And it requires a very, very sharp and astute knowledge of organic chemistry to remember the thing that's missing. Huh?
About cis trans.
Very good. This guy can also look like, it can go from looking like this to looking like this, and you can just be so unfortunate enough to perform the elimination like that. Very good. So, you got three products. 1, 2, 3. Does this have isomers, cis trans? No, because there's nothing on the other side. So, what's the major product? The trans doubly substituted double bond. This is major. What's the minor product? The cis. And this is the negligible product. Why is the major product the major product? Number one, yeah, but there's another phenomenon going on here. Phenomenon known as, the moment I say it, you guys remember it because Professor Navarro and Professor Greer, and I'm assuming the other organic chemistry professors here, are very big on the topic of hyperconjugation. Where the spinning of these hydrogens donates electron densities into the p orbital of the double bond, thus stabilizing it. And the more of those you have, the more stabilized the double bond becomes, the better the double bond, which is why more substituted double bonds are more favored. But substituted in what sense? Do we mean substituted in this sense, or do we mean substituted in this sense? Definitely not that one, because that's withdrawing from the p orbital. That's at war with the p orbital. We're talking about this. So we're talking about alkyl substitutions. Alkyl substitutions. All good? Any questions? Same rules of carbocation rearrangement apply. One more thing before we move on from this. I want you to name me the product. Name the product of an SN1 reaction between S2-butanol and methanol. S2-butanol and methanol. Oh, sorry. Hold on. S2-bromobutane. S2-bromobutane and methanol react in an SN1 fashion. Name me the product or products. Sorry,
I forgot what methanol is.
Yeah, methanol. So meth, one carbon, and then all alcohol. A one carbon alcohol. How you doing? S2-bromobutane and methanol. So first you got to know how to draw these things, right? Because if you don't know orgo to that level, you probably can't do it in your head. But that's what we want to be able to do. We want to be able to do stuff like this in our head. So let's draw S2-bromobutane. So here is butane, and here's 2-bromobutane. And if we go 1, 2, 3, and they go clockwise, in order for that to be S, we need the H to be in the front, so the Br needs to be in the back. That's S2-bromobutane. And methanol. Okay? Good? Did you get this far? Good. And then yeah, you got it, right?
Do we need to show the stereochemistry of the O?
Very good. At this specific position, when the methanol attacks the carbocation, there is a p orbital that exists perpendicular to the plane of the molecule, right? And that p orbital can be attacked from the front or the back. And if you attack from the front, you get the S enantiomer, you get the R enantiomer, and if you attack from the back, you get the S enantiomer. So this is plus minus, and over here is plus minus. So your two products are R2-methoxybutane and S2-methoxybutane. Methoxy, yes, that is called a methoxy group. That's your other consideration for the SN1 reaction. So we've done SN1 and SN2. We've done SN1 and E1. Next, SN2 and E2. SN2 requires absolutely no introduction. None. All right, so we need relatively strong bases. Relatively strong bases. Moderately. Right? And when we look at our pKa table later, we'll talk about what moderately strong bases are. But examples are Cn minus, SH minus, RS minus, OH minus, and this one's really dependent on temperature, right? F minus, what else? Yeah, I mean, this is a pretty decent list, right? Moderately strong bases and lower heat. SN2 means bimolecular substitution. Bimolecular nucleophilic substitution, right? Boom. That's it. It's the whole thing. Invert stereochem. Invert stereochem. No tertiary substrates. Why? Steric hindrance. In order to perform an SN2 reaction, you have to get to the antibonding orbital of the leaving group. And if something is tertiary, you can't get to the antibonding orbital of the leaving group, which means the reaction won't happen. Good. Perfect. My least favorite of the four, E2. Yes?
E1 and SN1, they happen simultaneously, no?
They do, but if you raise the heat, the E1 will happen more. Whenever you raise heat, elimination is preferred. So actually, what you're saying is a good point. When you do something like this, these are the products you get. Which is why organic chemists are so interested in purification. Because if you get that many products and you only want one, you got to figure out a way to get them away from one another. What's the best way to separate these? That's a great question. What's the best way to separate these? Well, first, I would do what? A separation. I would make an aqueous layer and a organic layer, and I'd separate these two.
How do we know what's going to be in the fluid?
Polar. Nonpolar. Then, to separate these, you can't. And then to separate these, I'd go by boiling point. I'd do a fractional distillation. I'd use a fractionating column, a very long one with aluminum foil so that it condenses and then falls back down and hits a certain boiling point. And then this one's probably going to boil out first, followed by this one, followed by this one. How do you separate these? You can't. I just said. At least we can't. I don't know if anyone else can, but. Okay, E2 elimination. By, huh?
Can you use column chromatography with the enantiomeric stationary phase to separate enantiomers?
Like an SBNAP sort of thing, like using some sort of so the R sticks to that. I don't know if enantiomeric stationary phases cling to common enantiomers. I know that you can prefer enantiomeric excess in product reactions by using R or SBNAP as a solvent, but I don't know about chromatography.
That's what I saw in the UWorld.
Really? Oh, interesting. Wow. Wait, bring me that question if you can find it. I would love to read their explanation about it. Okay. So E2 is bimolecular elimination. And it's either moderate bases with high heat or very strong bases. Or tertiary leaving groups. Or bulky bases. Which is why I hate it, because there's so many principles of inclusion. It's just like, oh, well, it's not this, so it must be this. Oh, no, you forgot about that rule, and that rule, and that rule, and that rule, and that rule. All right, so let's take a look at, one more thing. It is called an anti-elimination. So let's look at the most basic example of a beta elimination, or of a E2 elimination. Okay. Okay, that's fine. Good. NaOH and very high heat. The elimination has to take place how? Anti. The Br and the H that you eliminate must be opposite one another. Meaning that you can't just do that, because that's not anti to the Br. But that is. So you have to take that hydrogen. And then you have to fold these electrons over. And then you have to kick off the Br. But the question becomes, how am I going to write my product? Is my product this? Or is it this? And I don't know about you, but I'm not astute enough to tell you which one it is based off this elimination. So what I always did, well, in this one it's a little easier. I can tell you it's this. I can tell you it's the trans because these two are also opposite one another, the two methyl groups. But let's say you were doing this. Let's say so this is the most basic example, and your product is going to be this. but it could also be this because it can rotate. So either of them, the trend is going to be more favored. However, let's say you're doing an elimination that looks like this. And no, I'm not being a dick. I'm not being a dick. It's just an actual example of an elimination you could get. Huh?
Isn't that OH to the right?
pH, phenyl. And then the question that you're going to get asked, is the product cis or trans? Dude, I don't fucking know. What are you talking about? But yeah, figure it out. So the first thing that I always do is get the BR and the H on lines. Not on a wedge and not on a dash. Get it on a line. If the BR is coming out this way, we can rotate this 120 degrees and get it on a line. So let's do that first. We're going to rotate the right side 120 degrees. So we have H in the front, ethyl in the back, ethyl on a line, and then we have BR, which came down on a line, and if the BR came down, the pH is going to come up and out on the top. And the ethyl is going to, and the CH3 is going to go back. Does everyone follow that? Now, the BR and the H must be opposite. So the H must be on a line going up, which means we're going to fold it this way because it's going this way now. We're going to fold it like this. So the ethyl and the ethyl are going to come down. So next, when we rotate this way, ethyl and ethyl come down. H, BR, pH, CH3. And now people are like, well, Yusuf, you just wasted my time. Because why do I need to rewrite it like this? You know why you want to rewrite it like this? Because now when you do the elimination and you add the double bond, it literally shows you what's on the same side as what. The ethyl is on the same side as the phenyl, and the CH3 is on the same side as the ethyl. So the ethyl is the largest one here, and the phenyl is the largest one here, and they're on the same side, so the product is cis, otherwise known as Z. Same side, yeah.
It's the same size because both of them are wedge, right?
That's as complicated as the elimination will get on the MCAT. I highly doubt you'll see something like that, but it's important to know how they derive these sorts of questions. What's the other consideration? Cyanide is normally a base that does SN2, but that's not possible here because of steric hindrance. The cyanide's like, I guess I have to do elimination. Why did I just take that hydrogen? Because there's 3 of them. One of them has to be opposite the bromine. And in this case, it doesn't matter. So that's the tertiary leaving group, moderate bases with high heat. Very strong bases. It's fucking overkill. That's a lot of overkill. Absolutely unnecessary. But hydride is a really, really strong base. Also, sodium amide.
You can tell if it's a strong base or a negative.
Is that a strong base? Is this a strong base? Is this a strong base? No. Is this a strong base? Is this a strong base? No. Is this a strong base? Is this a strong base? He's pretty negative. No, so negativity does not mean it's a strong base. It's a strong base because of the fact that what? The conjugate is very, 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 very much not acidic. So why is hydride, why did I say this is overkill? Because what's the conjugate of hydride? Hydrogen gas. Does hydrogen gas act like an acid normally? No. But when you make it act like an acid, it gets really, really, really fucking mad. Sodium amide. What's the basic portion of that? It's the amide. What's the conjugate? Is that an acid? No, it's a base. You're making the base act like an acid. You think it's happy? No. And you can even go up a whole other step. It's not happy at all doing this. It's very happy doing that. So those are the very strong bases. Now the bulky bases. This fat fuck is lithium diisopropyl amide. Very bulky base, very large, cannot do SN2, so it does E2. However, David, since you're good at organic chemistry, and I want to put you on the spot, what's the product here?
Is there less substituted?
Yes, very good. It is the less substituted double bond product. Why? The base is bulky, is going to find the least populated area of the molecule to steal its hydrogen from. So instead of taking the hydrogen here, it will take the hydrogen here. This is called a what? A kinetic or a thermodynamic product?
Kinetic.
This is called a kinetic product.
Can't you force
Bulky bases, huh?
Can't you force it to be the thermodynamic by like changing the
Cool it down a lot. We'll make it relax a shit ton. And then that would become that. One more example of a bulky base. Anyone know? Big, big, big flashbacks to organic chemistry the moment I say the word tert butoxide. Potassium tert butoxide. Potassium tert butoxide. Potassium tert butoxide and LDA, your bulky bases. Also, this product of an elimination versus this product of an elimination, what are the proper names? Not cis-trans. What are the proper names? This is the Zaitsev product, and this is the Hoffman product. A Zaitsev and a Hoffman elimination. Well, that's it for leaving groups. Say goodbye. Any questions? Any questions? What time is it? That's the end of part 1. We're going to finish it all today, but I'm going to upload them in stepwise videos. Thank you for watching. Tune in for part 2.